So we know how material deforms elastically, and then we also came to understand about the plastic deformation. So today we will start with a more practical aspect of material deformation in terms of experimentation and the measurement of certain mechanical properties in the lab. So the basic and probably the most famous experiment in the domain of mechanical testing is known as tensile testing. And we will talk about this. So this test, it is not known how old the method of tensile testing is, but one of the old proof which is obtained is in one of the notebooks of Leonardo da Vinci, and you can find that image of tensile testing just by writing it on internet, and you will get a lot of information and also some of the research articles on the same topic. But we can make an accurate guess that tensile testing must have been much older than this, than the time of Da Vinci. And so we have discussed this in one of the tutorials also, but we will revive that again. So what we do in tensile testing these days is we make samples of certain dimensions, and the design of a few type of samples are very standard, and we will learn about the standard testing procedure of tensile test method also. So usually most of the samples can have thread at one end to fix this in the specimen, and then you have something like this. Then you have a radius of curvature here, and then again thread. So this is called dog bone kind of sample, dog bone sample, right? And so this cross section, the diameter here, you can call that initial diameter, and this length where the two edges are parallel is called the gauge length. Okay. So what we do is we fix this in the testing machine, and there are different types of testing machine. So you will have two columns, and there will be the upper frame, and then you will have two columns, and I'm just drawing the schematic, right? And the lower end can be fixed on the frame. So this is the lower part, and here you will have a fixture. So the fixture design also differs in different machines. Okay, so you can have something like this, or you can have, for this kind of sample, you can have screw kind of fixtures, but it can differ. So you will have a rod coming down and the counter part of the fixture on the lower side, and then here you will have pins, And so you put this, so this will be the fixture for the flat kind of sample. So the sample in 3 dimension will have a hole there through which the pin will go. So this will be the pin, and then you will have the gauge length part, and then again a hole, and the pin will fix the lower end also, right? So this part actually will look like something like this. So here you will have a hole, okay, and then you will have this gauge length, and this is a rectangular specimen. Then you will have another hole, the downwards hole there, right? And so this is how the specimen will look like. So in this case, this is my parallel length, so we call that the initial length, initial gauge length. And in this case you will have the cross section, so you will have this length into that dimension, so you can call this width, and you can call this B, or you can call it W1, W2, or whatever. So you can measure the dimension here and there, and then you can multiply, so that will be a cross sectional area. In this case the cross sectional area of course will be pi d naught square by 4, right? So before doing the test, it is important to measure the parallel length or the gauge length, and then the cross section, and you have to take measurement at different locations, so that you take the average value. Because of manufacturing, you will have the cross section, you will have a little bit of variation in the cross section, so you obviously have some amount of tolerance. If the tolerance is broken, then you will be making a lot of error when you measure the property. So what do we measure, and what property can we get from when we do the testing? So what happens in this testing machine is that, so by either hydraulic mechanism or by screw driven mechanism, you can pull this frame, the upper frame can move, taking this fixture along with this specimen upper part, because that is also fixed with the pin. So this whole thing will be moving up, so you will be causing an extension in the specimen that will cause a change in length, which will result in a strain. So you will have a change in length with time. So this sample will elongate, and then you will have this parallel length, the gauge length increasing from L0 to L, right? And this change therefore will be causing a strain in, so if this, so let me make a coordinate system for my tensile specimen. So this is my x1 direction and this is my x2 direction. So I will have the strain in x2 direction, which will be epsilon x2, let's say, and I should write ex2, not epsilon x2, and you know the difference. So instead of x2 I'll write e22, which will be delta L by L0, right? So this is my engineering strain, and we have spoken about true stress and engineering stress. We have also spoken about engineering strain and true strain. So true strain is not given by this, but true strain is given in the form of logarithm. So true strain, which is represented by the symbol epsilon, will be ln of, or the real logarithm of the final length. So let's call that LF divided by L0, okay? And you will see the difference of, so this is my true strain, okay? true strain. So what happens is, like, for example, we just take a cylindrical piece of material which has the initial length of L naught, right? Then we start testing and it expands, right? So now I have, so the length has increased and diameter has decreased, but we are not bothered about the diameter at this point of time. So now the length, let's say, is L1, okay, and then you test it further, you pull it further, and then the length further increases, let's say, to L2, okay. So let me make some differentiation here so that you can visualize that. So this was the initial condition, and this is after first deformation when the length changes from L0 to L1, and this is after second deformation when the length changes from L1 to L2, right? So what happens from this to this place? So what will be my engineering strain here? So engineering strain will be L1 minus L0 divided by L0, right? And then from here to here I will have engineering strain E. So this, let's call that E1, and this is E2 in the second step, and this will be equal to L2 minus L1 divided by L1, right? So what will be the total strain, total engineering strain we are calculating? So if we sum these two, so E is equal to E1 plus E2, that will not give me, so what if you measure the engineering strain taking this as initial value and L2 as the final value, which is the final value? So you should get actually L2 minus L0 by L0, but you will not get it by adding these two, right? So engineering strain concept is fails here to have a continuation of summation. But if you do the same thing with true strain, you will actually see that true strain converges here, so it doesn't fail, it follows the concept. So for example, if you have to calculate true strain from L0 to L1, so in the step 1, so we'll call that epsilon 1, that will be natural log of L1 divided by L0, and epsilon 2 will be natural log of L2 divided by L1, right? What will be the total strain? The total strain will be epsilon 1 plus epsilon 2, which will be, you know what it will be, so we can write ln A plus ln B is equal to ln A into B, so that will be L1 by L0 into L2 by L1, which is equal to ln L2 by L0. And so if you calculate taking this and this step only, the true strain, then you get the same thing what you get by adding stepwise between. So you can take infinite number of steps between the initial and final position and you will be getting the same thing, right? So this is the advantage of true strain. Now you can find a relation between true strain and engineering strain, not in elastic region but in plastic deformation. So in plastic deformation, when the material is deforming plastically, we know that volume is constant, okay? So what happens in elastic deformation? In elastic deformation, the volumetric stress was sigma h that is equal to bulk modulus into volumetric strain, right? So in plastic deform, so here because of Poisson's ratio not equal to 0.5. So for steels, for example, or for many metallic materials, the value of Poisson's ratio is approximately 0.33, which describes the relation between change in diameter and change in length. So because of this this relationship, you do not have volume constant in elastic deformation, but in plastic deformation the volume is constant. Okay, so in that case, in plastic deformation we can find out a relation between true and engineering stress. Okay, so our true strain epsilon can be given by natural logarithm of the final length divided by the initial length, right? And because volume is constant in plastic deformation, we have, so initially the volume will be Vi, which should be equal to Vf. So Vi is equal to the area, the initial area, Ai, into length, and this should be equal to the final volume, which will be final area into final length, right? So we can replace Lf by Li by Ai by Af. So epsilon will be equal to log of A initial by A final, right? So we can calculate this true strain using by measuring the diameter also. So you can take measurement at different locations and you can find the true strain at different locations, right? That can be done. So now let me break this. So this expression, or let me go to the next page and we can do it here, do it there. So